Hello, everyone. All right, now let's jump, to page 33, and let's look at the second sets of examples of holy hole principle. And the second set is going to be called the zero over zero problems. Okay, so zero over zero problems are not just bad, they're really bad, because what you have to do to solve a zero over zero problem is you have to do algebra. And typically, people are having difficulties when you have to do algebra. In our cases, if we want to compute the limits of those zero over zero cases, the core philosophy is you need to simplify algebraically your equations. For examples, for most questions for us, you will do this by simply manipulating fractions, by finding common denominators or etc. You might need to be doing some factorization if you have like the limits around a point giving a zero over zero problem of a rational function. And if you have radical terms, you might have to do rationalizations to simplify your equation. So, and then once you do your manipulations of fractions, your factorization or rationalization. You simplify, which typically means that you will cancel terms that you can do because you're inside the limit thanks to the holy old principle. And then simply by reevaluating your limit, you will typically get an answer for it. All right, let's just do an example right away. So our first example here, let's compute the limit as x approaches 2 of 1 over x minus 1 half, that's at the numerator, over x minus 2. Again here, the core philosophy stays the same. Let's just try to plug 2 in there. So you're going to get 1 over 2 minus 1 over 2 divided by 2 minus 2. So here I'm replacing all my x's by 2. Okay, so all the x's here are replaced by 2. And of course, what happens when you do the actual computation at the numerator, 1 half minus 1 half is going to give you 0. And then at the denominator, 2 minus 2, you're going to get 0 again. Okay, so this is not just bad, this is really bad. Okay, so you have to be doing something. So now I know I have fractions. So what I'm going to do is I'm going to simplify my numerator by adding those two fractions together. Okay, so here we go. So here my common denominator for the numerator, so between x and 2, is going to be 2x. So just by doing a cross multiplication here, I'm going to get, so this limit will become the limit as x approaches 2 of 2 times 1 minus x times 1, all that divided by 2x, all that divided by x minus 2. So the only thing I'm doing right now is I'm combining the two fractions at the numerator by using a common denominator, which is 2x, sorry. So I need to multiply the first fraction by 2 above and below, and I need to multiply the second fraction by x above and below. Now, if you simplify a little bit, you're going to get the following. So the limit as x approaches 2 of 2 minus x, that's for the numerator, at the numerator, over 2x divided by x minus 2. Now, if you have a fraction divided by something, you just need to take the x minus 2 at the denominator at the numerator. So you're going to get the limit as x approaches 2 of 2 minus x over 2x times x minus 2. So we're almost done here. So we can still feel the zeros, like this is what's giving me a 0 at the numerator. This is what's giving me a 0 at the numerator. So you need to simplify these two. So here what I'm going to do is at the numerator, I'm going to factor by minus 1 so that my x's where my 0 live will have the same coefficient, so which will be 1. So if I factor by -1, I have the limit as x approaches 2 of -1 times x minus 2, all that over 2x. 2x. No. Whoa. 2x times x minus 2. And here you can see it. So now this is the good part when things can simplify and cancel. So this x minus 2 here simplifies that one. And when that happens, because you're creating a new equation, when that happens, that's where the holy old principle is happening. So here you're getting a new expression, the limit as x approaches 2 of -1 over 2x. Now I'm going to plug 2 in it. I'm going to get -1 over 2 times 2, and that's giving me -1/4. So you get your answer by simply reevaluating your expression after you cancel your two zeros. And every time you cancel your two zeros, you're creating a new expression. Okay, and this new expression is not the same as the previous one. When you're simplifying things, you have to specify normally that you're canceling as long as x is not equal to 2. But that's something you can do in the limit because you're never at 2. You're around 2. Okay, so that's the idea here. So for this one, we get -1/4. All right, next example. We have to compute the limit as x approaches 2 of x squared minus 5x plus 6 divided by x minus 2. So again, for any limit, the first thing you do is you try it. Let's plug 2 inside and see what happens. So here, if you go 2 squared minus 5 times 2 plus 6, you're going to get 4 minus 10 plus 6, you're going to get 0. And then down there, if you go 2 minus 2, what a coincidence. We get 0 again. So you get this evil 0 over 0 bad case. So this is really bad. So we need to simplify this algebraically. So we have a rational function. We get a 0 at the numerator. We get a 0 at the denominator. For sure, we can simplify this somehow. So let's factor the numerator, because the denominator is already a linear term, which is x minus 2. So this is the same as the limit as x goes to 2. One thing that is kind of neat with factorization in the limit computation, because we know that it's 0 at 2, we know the first linear factor is going to be x minus 2. And the only thing we have to figure out is the other one. Well, the other one, since we know it needs to multiply to plus 6, the constant needs to multiply to plus 6, then we know that the second one is x minus 3, and you can double check. Minus 2 times minus 3 is plus 6, and minus 2 plus minus 3 is minus 5. And then this is all over x minus 2. And then, of course, you can see it here. Those two terms, they simplify perfectly. Okay, so you're going to get a cancellation here. And this x minus 2 over x minus 2. And those are the two zeros. This is where the 0 over 0 lives when you replace x by 2. So you're getting this new expression. So you're getting this new limit as x approaches 2. Now, after you cancel, you're creating a new expression. And this is thanks to the holy whole principle. So you're getting this new function. These two functions are not the same. And I have a remark that is coming up at the end of this example to illustrate that. Now you have this new limit, you have the limit of a new function, x minus 3, that you get after cancellation. So if you plug 2 in there, you're going to get 2 minus 3, and you're getting minus 1. So the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2 is minus 1. For that example, I want to show you what the equation x squared minus 5x plus 6 over x minus 2 looks like. So if I call this equation here f of x, if you draw this function, okay, this function is not defined at 2. If you plug 2 in there, you get a division by 0. But when you look at the graph of this function, after you simplify the x minus 2 at the numerator and at the denominator, you get x minus 3. So this function f of x is basically x minus 3, except at 2 where the function is not defined. So basically, there's a hole at x equal 2, and the height of that hole is actually minus 1, which is the value of that limit that we just computed. So here, what I've done for you is like, boom, here's the graph of f of x. So the graph of f of x here in blue, so is the line, looks like the line x minus 3, but at 2. So if you look at x equal 2, so if you look at x equal 2 here, the function is not defined at 2. There's a hole there. And basically, the name of holy hole principle was coined thanks to that example. Because when you look at f of x, this is like a common misconception that this equation, x squared minus 5x plus 6 over x minus 2, is x minus 3. No, it's not. This function, when you plug 2 in it before simplification, it's undefined. But what's the difference between the full line x minus 3 and that function f of x? Well, the full line would just go through like this, but the difference between the full line and the equation f of x is that they're almost the same, except for that hole here, and that hole at x equal 2 and y equal minus 1 is the difference between the equation x minus 3 and f of x. So the name holy hole principle is like, holy this function f of x is not x minus 3, it's x minus 3, but you need to remove one point, which is the point 2 minus 1. But even if you remove that point and that function is more complex, when you're computing the limit of f of x, because you're not at 2, you're writing the equation x minus 3 and you can compute its limit using x minus 3. It's so beautiful. All right, next example. So we want to compute the limit of the equation x squared minus 5x plus 6 over x squared plus 4x minus 21 as x approaches 3. So if you plug 3 in there, so first thing here, let's plug 3 in there and see what happens. Okay, so if you plug 3, just wait and look for my pen. So if you plug 3 in there, you get 3 squared minus 5 times 3. I mean, you can kind of foresee what's going to happen here. If you're not getting 0 over 0, it's boring. Okay, so plus 6. So you're getting 9 minus 8. So yes, you're getting 9 minus 15 plus 6. Whoa, we get a 0 here. And then what about down there? So you're getting 3 squared plus 4 times 3 minus 21. So you're getting 9 plus 12, which is 21 minus 21. What? Okay, so you're getting 0 over 0. Super bad. Okay, so bad limit. So we need to simplify. Again here, simplification means we have a rational function. It's factorization. So let's factor. And again here, because we know the roots, we know that 3 is a root at the numerator and denominator, this is a factorization question, but it's an easier one because we know the first factor for the numerator and the denominator is going to be x minus 3. And we just need to figure out the other one. So here we get x minus 2. It's the same as the previous one, actually. So minus 3 times minus 2 is plus 6. And then for the denominator, we want minus 21. So we're going to get x plus 7. And now here we go. We get this nice simplification, x minus 3 and x minus 3. This is where the 0 lives. So you're getting a new expression. After simplification, you get the limit as x approaches 3 of x minus 2 over x plus 7. So after simplification, you're getting a new equation that is not equal to the previous one, but that new equation will have the same limit as the previous one. And that new limit, you're going to get it just by evaluation. So you're going to get the limit as x approaches 3. So if you, if you evaluate here, you're going to get 3 minus 2, which is 1 over 3 plus 7, which is 10. And you're going to get at the end 1 over 10. And that's the value of your limit. So if you get a 0 over 0, after you do your direct evaluation and your function is rational, you have to do factorization, cancel the common factors that comes kind of for free here, and then reevaluate, and then you get the value of your limit.